Today we are breaking down the most ambitious capital deployment in Elon Musk's history, and what it would mean for the semiconductor industry, for artificial intelligence, and for every company competing to control the infrastructure of the next technological era. Documents filed in Grimes County have placed the potential full-scale cost of Terafab at $119 billion, a figure that has grown from the original $25 billion announcement made in March 2026. Nearly half, approximately $55 billion, is allocated to the initial development phase, with a $3 billion research facility already under construction in Austin. If that figure reaches its stated scale, Terafab will not simply be another chip factory. It will be the largest single manufacturing infrastructure commitment any private company has ever attempted. And understanding why Musk is willing to make it reveals something fundamental about where the AI race will actually be decided. The case for Terafab begins with the chip demand problem inside Musk's ecosystem that is larger and more structurally constrained than most observers recognize. A modern Tesla vehicle is not primarily a transportation product. It is a real-time AI inference machine that processes camera input, classifies objects, predicts surrounding vehicle behavior, and executes driving decisions with latency measured in milliseconds. Scaling that to millions of autonomous robotaxis operating continuously requires a volume of specialized AI chips that, according to Musk's public statements, the current global semiconductor supply chain can provide at only approximately 2% of what the combined Tesla, SpaceX, and xAI ecosystem is projected to require. The Optimus humanoid robot compounds demand further. A robot operating in unstructured environments must maintain balance, control dozens of mechanical joints with real-time precision, and respond to unpredictable human behavior. Compute requirements orders of magnitude more intensive than basic driver assistance. SpaceX's Starlink ambition adds a third vector. Future network architecture envisions satellites running AI inference in orbit, rather than relaying raw data to ground stations, which requires a specialized chip class designed for radiation, thermal extremes, and strict power constraints. xAI's large model training requirements represent a fourth. The aggregate chip demand across all four entities is the structural reason Terafab exists. The strategic logic follows a pattern Tesla has executed before, most directly with battery technology. When cell supply became the critical bottleneck for EV production, Tesla did not remain dependent on Panasonic indefinitely. The company partnered, absorbed manufacturing expertise, and ultimately developed the 4680 cell, optimized for Tesla's specific requirements rather than the broadest possible customer base. Terafab follows the same logic at substantially higher technical difficulty. Semiconductor fabrication at leading-edge nodes requires ultra-clean rooms, extreme ultraviolet lithography machines priced at several $100 million each, atomic-level process control, and yield optimization expertise that major foundries have spent decades developing. This is precisely why Intel's involvement is strategically significant beyond any financial contribution. Intel brings operational fab experience that cannot be replicated through capital spending alone. The institutional knowledge of running high-volume wafer production, managing defect rates across millions of cycles, and translating chip designs into consistently manufactured physical reality at the yields required for profitability at scale. The chip roadmap Terafab supports covers two distinct technology philosophies. The first is the AI processor lineage for Tesla's terrestrial ecosystem, the AI5, AI6, and AI7 generation sequence. AI5, confirmed by Musk as tape-out complete ahead of schedule, begins limited production in 2026 and enters mass production in 2027, delivering approximately 5 times the useful compute of the dual AI4 configuration currently in Tesla vehicles. AI6 and AI7 follow as rapid performance iterations across the full self-driving, robotaxi, and Optimus platforms. The second philosophy is the D3 space-grade lineage, engineered for Starlink's orbital environment. D3 chips must withstand intense radiation, extreme temperature cycling, and the strict power constraints of satellite hardware. Requirements fundamentally incompatible with the performance-first design priorities of terrestrial AI processors. Two parallel chip families reflect the operational reality that Musk's ecosystem spans two physical environments, each demanding different engineering trade-offs at the silicon level. The most architecturally unusual aspect of Terafab is not its scale, but its intended operational model. In the conventional semiconductor industry, chip design, wafer manufacturing, AI training, and product deployment each cross organizational and geographic boundaries, making each optimization cycle span multiple quarters. Terafab's design intent is to compress that cycle by co-locating chip design, fabrication, AI training infrastructure, and vehicle or robot testing within a physically integrated ecosystem adjacent to Giga Texas. Real-world performance data from operating Robotaxis or Optimus units flows into xAI's training clusters. If analysis reveals the limitation is in chip architecture rather than the model, inference latency, sensor bandwidth, power consumption, the design is adjusted, prototype wafers produced, and new chips redeployed into test vehicles at a speed the distributed conventional model cannot approach. The stated production target, beginning at 100,000 wafer starts per month and scaling toward 1 million per month at full capacity, which would represent roughly 70% of TSMC's current global output by common industry comparisons, reflects the volume required to sustain that closed-loop development cycle at the scale of Musk's full ecosystem. The $119 billion figure, viewed in isolation, invites legitimate skepticism. Tesla has never operated an advanced semiconductor fab. The gap between announcing a chip factory and producing leading-edge wafers at competitive yields is measured not in dollars, but in years of operational learning that even established foundries cannot accelerate indefinitely. The 1 terawatt of annual computing capacity Musk has described as a long-term target, which, at 250 watts per chip, would require approximately 4 billion chips per year, is a projection of ambition rather than a near-term production commitment. The most accurate framing of Terafab at this stage is what Musk himself has suggested. The Giga Texas phase is the starting point, not the entirety of the project, a design and test hub where Tesla learns to produce chips optimized for its specific requirements before attempting production at a scale that would reshape the global supply chain. Whether the $119 billion figure represents a realistic, long-term build-out or an upper-bound planning scenario for a decade-long project, the strategic logic is clear. In an industry where AI capability is increasingly constrained not by model architecture but by chip availability and manufacturing throughput, the company that controls its own supply of purpose-built silicon controls the pace of its own evolution and potentially the pace of everyone else's as well.